It's really a big honor to have with us Costas Pelekanakis. Costas received his diploma from the Technical University of Crete in Greece in 2001 and his PhD from the US in 2009. From 2009 to 2015, he worked with the Acoustic Research Laboratory at the National University of Singapore as a research fellow. And is currently a senior scientist at the NATO Science and Technology Organization, the Center for Maritime Research and Experimentation in La Spezia in Italy. He was awarded the MIT Presidential Fellowship in 2001. In 2018, he was the co-recipient of the NATO Scientific Achievement Award. And in 2019, he was the co-recipient of the IT Premium Award for the best paper in radar, sonar, and navigation. So today, Costas will talk about the next milestone, adaptive and secure underwater acoustic communications. And as usual, there is a Q&A session at the end of this seminar, so you are definitely cordially invited to do your question, to post your question on the panel, and at the end, Costas is happy to reply to your question and to have any discussion. So thank you so much again, Costas, and I think you can start.
Thank you, Julia, for the kind invitation and the kind introduction. It's really a pleasure to be an honor to participate in this webinar. Let me try to share my screen. Share. I believe you can see my.
Yeah, we can see. So just we move to.
Let me. So now you can see.
Perfect.
Let me arrange the. Okay. Well, before I start, let me also wish good luck to the newly established Technology Innovation Institute that you guys now you count more than, well, about 1.5 years of lifetime, and it's well, best of luck with your activities. And actually, I'm really delighted to see that you are interested in underwater communications, and well, hopefully, and I'm looking forward to seeing some great research coming from that side of the globe. So regarding the presentation, well, the idea is to talk about adaptive and secure acoustic communications, as I consider it two hot topics currently in the field, and with a lot of opportunities for innovation. That's why I call it as next milestone. I will start by describing a little bit of the current state of the art of underwater acoustic communications. And then I'm talking to an audience that is very mixed, like some are very maybe knowledgeable about ACOMs, but some are maybe very new. So it's good to have, let's say, a first introduction on the state of the art of underwater acoustic communications. And then I will talk about two open problems, adaptive communications and the application of machine learning to at the physical layer, and physical layer security. So let me start by describing to you what is the performance of today's underwater acoustic modems. So if someone wants to buy an acoustic modem, you know, what is the bit rate that he can hope for? And so here you have a table. Let me see if I can also have the pointer here. Okay, so you can see, I believe you can see my mouse. So here you have a table that summarizes a few companies and their associated products. You can see the modems coming from some NATO or Evologix and so on. You can see the band, the bitrate that they advertised, and the modulation technique. So I mean, by no means this table is not meant to be exhaustive. It's just to give you an idea of what's happening in the technology sector right now. And by looking at this table, you see that I mean, the companies typically divide the products into two categories. So you have modems that rely on incoherent FSK, which is supposed to be a very robust scheme and can work in a variety of environments, shallow environments or deep water environments, horizontal or vertical configurations. And typically with FSK, you get about tens to hundreds of bits per second. And then if you want to go faster, then the company will sell you a different modem, which may rely on FDM or an equalization or spectrum. And this modem can go to tens of kilobits per second. So this is more or less what you get right now from the companies. And actually, it is interesting to see that there is a range rate bound that applies to most of the modems in today's technology. Actually, and this plot was published in 2000. And what you see here is in this plot you have a plot of range and data rate, and you have a graph here, which is range rate times 40 kilometers times kilobps. So basically, what this plot says that most of the systems that were reviewed in that paper were under this curve. And actually, what happens today is actually also this is true also today in 2021. Also, you see that most of the modems are actually below this performance bound. So this range rate bound says that if you, for example, if you want to shoot for a 10 kilometer, let's say if you want to shoot for 40 kilometers range, then your performance will be below 1 kilobps basically. So if you by just looking at these numbers, if you have a quick comparison between underwater ACOMs and 4G, you can see that, okay, the bandwidth that you go for the acoustic modems are less than 40 kilohertz. For range is about 1 kilometer. You don't expect to have a rate of more than 40 kilobits per second. While on the other hand, in 4G, you can contrast the bandwidth, 20 megahertz, and the rate is in the order of 10 megabps. So why this is happening? I mean, there's an easy, there's something that is happening in acoustics that is not actually happening in radio comms, and you have a range, you have actually the bandwidth is range dependent in the sense that because you have frequency dependent absorption, and that absorption increases quadratically with frequency, this limits a lot your operational bandwidth. As you increase the range, you need to decrease the bandwidth. So this is the main reason why you have less bandwidth and less rates in ACOMs than 4G. But also there is also the reliability. The reliability actually is also very different. You have more reliable comms in radio than in underwater acoustic communications. And why is that? Well, I'm trying to give you with this table, try to summarize some of the key differences between acoustics and RF. And you can see, I can start by this propagation speed, which is, you see the propagation speed in radio is 5 orders of magnitude higher than the propagation of speed in acoustics. So if you are looking for a signal delay at 15 kilometers, it's almost 0 in radio, and you have 10 seconds in acoustics. So you really have to wait a lot of time for long propagation delays. Then if you look at, and this, of course, this delay is an important factor in networking. So for example, if you have high latency, then immediately the throughput of the network goes down. If you look at the pulse compression, which is basically pulse compression or dilation, which is basically the ratio of the mobile speed over the propagation of the wave. For typical mobile speeds, you see that this ratio is 10 to the minus 7, while for acoustic, underwater acoustic, this ratio is close to 10 to -3. So you can immediately see that it's negligible in radio. It's not negligible in acoustics. You really need to account for pulse compression or dilation, and this gives a burden to your receiver. Another thing is the ratio of bandwidth of the carrier frequency. You can see it's 10 to -3 for radio. So this considered the radio channel is easily considered as a narrowband, not in the acoustic domain, which is ultra wideband. So this immediately poses problems in how to model the channel actually, because the fading statistics are frequency dependent on the acoustics. On the radio, you can actually focus on the center frequency and rely on that, to do the measurements of the when you do the channel modeling. Another important aspect that affects the receiver is the multipath spread. You see, typically the multipath spread is 1 microsecond in the radio. In the acoustics, it can go from 10 milliseconds all the way up to seconds. So if you translate that into the number of channel parameters or coefficients that you need to estimate when you do channel estimation, typically for radio is about order of 5 channel parameters, while in the acoustics you need to go from 100 to 1,000 parameters. And this is, again, brings a lot of complexity into your receiver at the physical layer. And last but not least, you have the noise. Typically is non-dynamic in the radio, while it's very highly dynamic and environmental in the acoustics. So one certain thing that we can say that copy-pasting solutions from RF to the underwater domain simply doesn't work. And actually, if you just to give you an idea of the brutality of multipath in underwater acoustic comms, on the left here, you see the transmitted pulse, which is a linear LFM that goes from 10 to 15 kilohertz, and the duration is 1 second. The color bar here is in dB, and that LFM was transmitted in a real channel. The range was about 1 kilometer, the sea depth 100 meters. And here you see the reception, and this, what you observe here is actually the multipath, the echoes at the receiver. And you can easily understand that, of course, they are time varying and frequency dependent. And actually, you can see from here that they last more than a second. So this is actually very, very brutal multipath conditions. So another thing that is happening right now when it comes to standards. So in the RF, you have all these standards about outdoor and indoor environments at various bands and ranges and MIMO or non-MIMO technology. But in the underwater, you don't have any standardized models. And of course, that impacts the work we do in the underwater domain, because we don't have a unified way and agreed by many to assess different solutions. And standardization is one of the reasons that the pace of the development in RF comms has been accelerating over the years. But what about the interoperability? Of course, in the radio world, you have iPhone and Android, and they can talk over 4G and 5G and whatnot over the Bluetooth and Wi-Fi. In the underwater domain, you have only one interoperable waveform, and this is called Zenius. It is well, that was funded by NATO, that activity, but is open and free for NATO and non-NATO entities. And Zenius currently is the only digital underwater communications, acoustic communication standard that exists right now. Just one slide about Zenius, just to give you a brief, very, very brief introduction about Zenius. So what you see here, this is the generation of the waveform. This is the block diagram. So you have the user bits, and the bits basically are coded by a half-rate convolutional encoder, and then they went to the modulator, which is what it does is a frequency hopping binary frequency shift keying modulation. And you can see the Zenius waveform here is the spectrogram of the Zenius waveform On the right, you can see the frequency band, which is about 4 kilohertz with the frequency, the center frequency is 11,520 hertz. Here, this is the waveform here is the Zenius baseline waveform without any additional cargo. Here is Zenius with cargo. I welcome you to visit the website, januswiki.org, and become members. It's open. And this is one way to actually download material about Zenius and also code and start doing the development in your lab. And also, this is also a good way to participate in the overall development and shaping of Zenius. So, what is the current trend in the underwater acoustic domain? Now, for the last 10 years, there has been a transition from monolithic to software-defined modems, and this is, you can see, if you see the publications in the data coming from academia, now they're focusing on software-defined modems, and why this is the case? Well, at the physical layer, you need to be flexible and aim for different rates depending on the channel conditions, range, application requirements, and etc. Also, we need flexibility at the networking level, where we need to apply different MAC and routing solutions depending on the network topology and the number of nodes, and we need to do that efficiently. And in order to do that, we need to have some cross-layering implemented on that. There are numerous applications, especially military, that require the transmission of sensitive data. And so applying authentication, cryptography, and traffic monitoring are things that can be accomplished in only when you have software-defined modems. And last but not least, you have you can combine communications with other services, such as navigation, for example. So because note that GPS doesn't work underwater, so in order to have navigation with comms, you need to you can timestamp the packets, and based on the transmit and receive the reception of the packet, and you can extract the time of flight, and there you go, you can have localization in underwater. So these are just to give you an idea of indicative publications on software-defined modems that in the last 10 years. This is for your awareness when you look at the slides offline. So what are the open problems now? What are the open problems in the arena of acoustic communications? So first of all, we need flexible and software architectures that will enable all the different solutions that we want to apply for all the in all the layers of the OSI stack. And so this is something that is happening right now. The software development is crucial and is a hot topic. At the physical layer, how do you incorporate MIMO technology on hardware? How do you do adaptation and feedback exploitation? At the networking level, how to tackle high latencies, and how do you ensure node connectivity in different topologies? So security is also a hot topic, because we need now, since we are talking about software-defined modems, we need to consider all the different attacks that are happening in the OSI stack, and how to ensure connectivity and sustainability under attacks. This is also a hot topic. Multimodal systems, like combining acoustics with other modalities such as optical and RF comms. This is also something that is happening right now in the field. Typically, you envision that you will have an optical link that will transfer megabits per second in 10 meters or so, or tens of meters. But if you want to go to kilometers, then you need to switch to acoustics. And last but not least, how the new tools of machine learning can help us to communicate in very challenging environments, and where closed form solutions don't exist. So that was more or less an idea, a brief introduction of the state of the art of underwater acoustic communications. And now I would like to move to two topics that I consider hot at this moment. And well, the whole point is to spark a discussion on these topics. I'm going to present some preliminary results, but definitely there is a lot of room for innovation and a lot of things to say. So here is the moving to the adaptation. Like the scenario of interest that I'm interested here is the scenario of interest that I'm interested is you have a modem, you have a software-defined modem. It can choose between n waveforms, and every waveform can achieve its own bit rate. You can imagine that you can have bit rates from very low to very high. And the challenge here is to choose a signal given the current channel conditions that meet certain requirements. For example, it could be choose the fastest signal such that it meets a BR constraint, a bit error rate constraint. And you can see, I mean, here is an example of a channel and a reception, and you can see here the reception of the communication signals, and all of a sudden a boat is passing by. You have immediately some extra noise, and so how do you react to that? So this is a typical scenario where you need adaptive communications. So here in this presentation, I'm tackling the issue of BR computation or BR prediction. And the BR of a communication system is basically affected by three factors. You have the signal parameters here, modulation, baud, code rate. You have the channel parameters. It can be the input SNR, the Doppler spread, delay spread, and so on. And you have the receiver parameter, which is basically the receiver front end. It could be FDM, it could be equalization. You have the decoder and the interaction between the front end and the decoder, and so on. Now, typically, I mean, the BR, if we go to textbooks, you have closed form solutions, but these closed form solutions depend often on non-realistic assumptions about the statistical channel model. One major issue is, for example, stationarity. I mean, in real channels, you have time-varying statistics. Nothing is, stationarity is very, let's say, short-term. So how do you compute the BR when basically you don't know the statistics, or the statistics are, are very hard to derive? And on top of that, in underwater, if you don't have widely agreed channel models, how do you, come up with BR expressions that, you can persuade many that this is the right thing? So it's a very tedious issue to have closed form BR expressions. So the approach that one way to tackle the problem is to have a purely data-driven approach based on machine learning. And the idea here is to regress the BR from some parameters, some inputs, they take a machine learning algorithm, train it based on some inputs, and magically it can give you the BR estimate. So the machine learning approach that we are proposing here is so-called the regression trees. So as basically the name suggests, it tries to regress the BR, and I will try to explain how this happens in using a toy example. Imagine that you have here the BR as a function of two inputs, x1 and x2. And here is your space, the inputs x1 and x2. What the regression tree will try to do is it will try to bisect the input space into regions. And this bisection is done iteratively and under an optimization constraint such that at the end of the day, you want the minimum square error of the BR prediction to be the minimum. So what it does, so the regression tree will, using the CART algorithm, it will bisect this the space, the x1, x2 space, into these regions, and in each region it will basically map the average. It will compute the average BR. So this is basically what it says, that if your x1 and x2 is in this region, your BR is the average BR of that region. So if you trace, this is again, if you trace the decision tree in this plot. So it goes like that. If your x1 is less than the threshold T1, you move to this node, and if x2 is also less than the threshold T2, so basically you are in this leaf, and this leaf is the BR estimate. And you can also traverse the tree in the other nodes, and so on. So the leaves of this tree is which is the mean BR being in this area, is basically your regression, your output. So the nice thing about what I like about the decision trees are two things. One is the interpretability. I call them the decision or the regression trees is the same when you have a continuous variable to deal with. They are called regression. If you have a discrete variable, they are called also decision trees. But there are two features that I really like about the decision or the regression trees. One thing is that they can take as input parameters categorical parameters, such as, for example, 2 PSK or 4 PSK, 8 PSK. These are categorical parameters, not continuous parameters. And the other thing is the interpretability. You can actually interpret the decision, the regression tree very easily by eyeballing the leaves and the nodes. Of course, and also there is a lot of open software in Python. It's called scikit-learn, and you can apply many techniques there, and they're coming for free. So here is an application of the regression tree in real data. So here this is how the tree looks like after training. And you can see it discriminates between the input parameters here, the SNR and the delay spread. And at the end of the day, at the leaf, it will give you the BR estimate. And what is also nice is that the decision tree can be exported as a, let's say, a text file, which is a bunch of if then else statements. And this is extremely easy then to program it in C or Python and work, for example, with embedded computers. So, and you have extensions of the regression trees, which are called boosted trees, and actually what they are is a linear. Actually, they are a linear combination of regression trees. And why we do that? Why these? What is the effect of the boosted trees? They try to reduce the variance of the estimate of the BER, and they do that by, let's say, summing uncorrelated random variables. And there are many, there is software, open software that allows you to choose these weights adaptively. This is called AdaBoost. And it's very helpful also in that regard. So if I move on, this is more or less, this slide tries to give you the frame of link adaptation using supervised machine learning. So you are sitting at the transmitter and you have the feedback link. So this feedback is coming from the receiver. From this feedback, you can estimate the current channel conditions. You assume also that you have a database of past transmissions that you rely to model, to train the machine learning algorithm. So having basically the trained model and the current channel conditions, the machine learning will tell you the BR estimates of all different signals that you want to apply. And then you can basically, based on these estimates, these predictions of the BR, you can switch or you can choose that rate that falls below a BR threshold that is can be application driven, and you can then choose that signal to go to the forward link. I mean, there are two issues here with adaptivity. One is the feedback link. It could be the case where, depending on the range, it could be the case that when you start measuring the channel may be outdated, because by the time you send the signal to the receiver in the forward link, the channel may have changed significantly. Another issue is what if you operate in an environment that you've never seen before? So it's important to have this database of past transmissions to be diverse enough to include many different environments. Because from here you will learn the statistics, and this is actually what the machine learning does. It basically learns the statistics of the channel and tries to come up with a BR prediction. So let me also give you some results of applying boosted trees. Here is we are in the Gulf of La Spezia. We're looking at an experiment that happened in 2017. Here, La Spezia Harbor. This is the area of the experimentation. The depth is about 10 to 12 meters. The signals occupy the 8 to 12 kilohertz. We had static links, various ranges. And these are the transmission modes. These are the different signals that were transmitted. You can see you have different modulation scheme: BPSK, 8PSK, QPSK, 8PSK. You have different encoders: half rate convolutional or half rate trellis coded when you combine it with QPSK, or 2/3 rate trellis coded when you combine it with 8PSK. We had also spread spectrum on top of it. So we applied different spreading lengths and different baud rates. So at the end of the day, what we cared is to have a variety of bit rates from very low, from 13 all the way to 466 bits per second. Why we aimed for low bit rates? Because the scenario of interest is to operate in very low SNR environments. Just to give you a glimpse of the harbor conditions, here is you see we have different, because we operated over 5 days. We also encountered different weather conditions and different sea waves, and so it's important also to stress that. Also, because we are operating in a harbor environment, we had ship propeller noise affecting the transmissions. So from time to time, ships or speedboats were passing by, creating extra noise. So at the end, we managed to get 3,700 for received signals, and you can see the average input SNR at the input. I'm talking about the input at the receiver for all the different receivers that we had in the experiment. Here's a histogram of the SNR, and we played the game in post-processing. So we took the signals and we added white Gaussian noise in order to reach an SNR at 0, -5, and -10 dB. So basically, we were adding extra noise on top of the received signal in order to reach the 3 different regimes of -dB, 0 dB, -5, and -10 dB SNR. And as I said, we did that because we wanted to see performance at very low SNR communications. This table gives you the average BR of all the different signals we tried. You see from low bits per second for 13 all the way to 466. You see also the number of signals that were processed for its rate. And you also see the average bit error rate for 0 dB, -5, and -10 dB. Well, as you expect, the average BR is lower in 0 dB as compared to -10. This is something that it was expected, but also note that the minimum BR is not actually at the smallest rate. Actually, this is something that is happening in real life when you transmit different signals at different times under different channels. You cannot have a very fair comparison between the signals themselves. Also note also you have different number of signals that were transmitted. So it's not that the smallest bit rate will give you also the smallest BR, but this is reality. But actually, what we try to do here is to have a machine learning algorithm that tries to learn these BRs. So overall, the BR was ranged from 0.0046 to almost 0.5. And as I said, we try to make a machine learning working or predicting these BRs on this data set. So after processing the data, we generate the database, and this is basically how the database looks like. You can see that for every row of the table, you have the constellation, the input SNR, and channel parameters such as delay and Doppler, and the BR. So you stack all these measurements in a table, and then you start. Then the training phase of the boosted tree comes. So what you do is typically you split the data into 70% you use them for training, 30% for testing. You can also randomly split the testing and training different times. So the whole point is you need to be also careful so that you don't do any overfitting on the boosted tree. So after doing this, after doing 50 random splits of the data with 70% training, 30% testing, and using 100 constituent trees, the minimum square error of the BR prediction was close to 10 to -3, which is a pretty good result. If you see that the average BR range from 0.046 to 0.5, this is a very good actually accurate prediction of the BR by the boosted tree. And then what we did is we played a game in post-processing. There is no real-time feedback here. So we wanted to see what is the gain of the adaptation in the testing set, which is the 30% of the data. So in this 30% of the data, we use the trained boosted tree, and we try to measure the throughput, where the throughput is given by this expression is the number of successful transmissions over the total number of transmissions times the signal bit rate. And here, what you see on the right is the effect, basically are the results for the different for the adaptation and for the different schemes, for the different modulation schemes. What you see here, for example, if you take this picture, this plot, we are targeting basically the SNR to be less than 0 dB. So you have all the signals there from all the signals -10 and -5, but also we have also constraints on the BR. So basically here, if you focus on this plot, the idea is to understand if you want to have, if your target SNR is below 0 dB and your target BR is 10 to -3, what is the average throughput of your link? And you can see that when you do adaptation, it's much higher than having a fixed rate transmission scheme. And we apply this game of what if your target SNR is -5 dB? and also for given target BR constraints, what is the average throughput? And you can see overall that adaptation gives 10 to 20 times faster throughput as compared to a fixed rate modem. So this is as far as adaptation and application of machine learning to the physical layer. And now I will move on to the next section, which is physical layer security. So we're interested in the following working scenario. You have two legitimate nodes, Alice and Bob. They are authenticated, and they wish to establish a secure communication. And the third node, Eve, is a non-legitimate node who listens to the signal exchange between Alice and Bob. And the goal is to ensure message confidentiality. In other words, we don't want Eve to extract the actual information being sent by Alice and Bob. And of course, you need to make some assumptions about Eve's intelligence there that I will explain. So we are focusing on symmetric cryptosystems because they come very handy for ad hoc topologies. If you had asymmetric cryptosystems, then you need to have a central authority to distribute the public keys. And this is something that we prefer to avoid because a central node is a single point of failure. It could be also under attack. So it's more flexible to have in ad hoc topologies. It's more flexible to deal with symmetric cryptosystems. So what does the symmetric cryptosystem? You have a message, which is typically referred as the plain text. This plain text is converted to ciphertext through the application of an encryption algorithm, say the advanced encryption standard, with the application of a key. And once the ciphertext is produced, it's transmitted into the water, and Bob from the other side transforms back the ciphertext to a plain text through the inverse application of the decryption algorithm, and applying also the same key. So there are two challenges associated with the key management. The first one is, how do you share the keys when a new trusted node must join the network and does not have any preloaded keys? And the second challenge is, in the event where one node is hacked, then the entire network is not secure anymore because Eve has access to the current and future keys. So, I mean, typically in symmetric cryptosystems, since the keys are preloaded, if you know one key, then you cannot basically then you know basically all the keys that are going to be applied in the future. So the entire network is compromised. So how do you tackle these two issues? So we propose to have physical layer security for that. And physical layer security aims to generate a key between Alice and Bob without the need to share the actual key. And in theory, this is possible due to channel reciprocity. Yet in practice, reciprocity is hard to achieve, especially for kilometers of range, and also when there is platform mobility. So consequently, the name of the game shifts towards ways to exploit the correlation in the bidirectional link between Alice and Bob. And we also assume that Eve cannot be right next to Alice and Bob because she needs to stay covert. So how would you use VLS in a network? Here you have, for example, Alice and Bob. Alice is part of a secure network, and Bob wants to join this secure network. You see the blue arrows mean secure links. The red arrow means unsecure link. And here you have Eve. So after applying PLS, Alice and Bob ideally they generate their own key, and then in the next phase, so this is also a secure link, and so Alice can also transfer the preloaded keys now to Bob, and now Bob is part of the network after getting all the keys from Alice. So this is how you can apply PLS in a network scenario. And how does it work? How PLS works? You have basically four steps that you need to apply. In the first step, Alice and Bob exchange a pre-agreed number of channel probes, and from these probes, they independently generate some pre-agreed features. In the second step, you have the quantization, where now the features are quantized between Alice and Bob. And at the end of the day, you have a vector of quantized bits. And you can imagine that these quantized bits become the precursor of the key. In the third step, you have the, since you expect that Alice and Bob will not have exactly the same quantized bits, you need to have some reconciliation. So there's some data exchange here in order to reconcile the bits. But since there's a data exchange and Eve could know about this data, you need to have an extra step which is called private simplification. And in this, at this point, we assume that Bob and Alice have reconciled their bits, and we need also to ensure that Eve cannot exploit the information transmitted in the reconciliation step. So at the output of the private simplification, you have the crypto key that you are looking for. So in the first step, as I said, Bob and Alice exchange a number of pre-agreed channel probes. So here the channel is represented the channel is a complex vector. So this is the impulse response of the channel. And this, of course, can be measured in different ways. You can send the probe signal, and you can match filter on the probe signal. You can be an LFM or a BPSK sequence, and you can estimate the channel. But at the end of the day, what the channel is an LTAP complex vector. And then from this vector, you can start thinking of features, like features that stay between Bob and Alice. They are symmetric, like very, very correlated. And of course, that is also a hard process because, for example, the phase of the channel really changes very fast. So you cannot rely on the phase of the channel, but maybe the amplitude and the delays of the different multipaths, these tend to stay fixed for some time, and you can hope that you can generate the key based on these features. So here we have four features that we try. We have the L0 norm, the channel sparseness given by, which is a combination of L1 and L2 norms. You have the L2 norm here, and you have also the maximum delay spread of the channel. So these are features that are generated or extracted by the impulse response. And then we need to quantize them. And each feature is quantized based on link-dependent quantization levels. And these levels are a function of the mean and the standard deviation of each estimated feature. So in order to do that, in order to estimate the mean and the standard deviation, we need to devote the number of features, a number of probe exchanges in order to estimate them. And as soon as you have the mean and the standard deviation, you can start applying quantization, the quantization intervals, and then you get the quantization vector at the end. So note that since mu, the mean, and the standard deviation are channel dependent, they may be different between Alice and Bob. The actual values of mean and standard deviation may be different for Alice and Bob, and of course also for Eve. So let me So a few results regarding the channel probes and how this reciprocity applies in real life. Here you have we are in off the coast of Portugal. You have Bob here, which is a drifting ship. You have a buoy, which is Alice, and Eve, which is an array. And you can see that the experimental setup, the Alice-Eve distance, the Alice-Bob distance. The probe that Alice and Bob exchanged was an upsweep chirp, and the duration was 1 second. This is the bandwidth. And the exchange between Alice and Bob was every 10 seconds. And you here you see I want to show I want you to understand the correlatedness between the impulse response between Alice, Bob, and Eve. So overall, we have 187 probes transmitted over an hour. You can see the different depths of Alice, Bob, and Eve. Eve, of course, is aware of the way that you estimate the channel because he's using the probes that Alice and Bob exchange. And you can see here you have the results of Alice. This is the link from Alice to Bob. This is the probes are stacked chronologically over the y-axis, and x-axis is the multipath delay spread in seconds. And so here you have the variation of Alice to Bob link over time. And this is the variation of Bob to Alice link over time. And this is the link from Alice to Eve and Bob to Eve. And you can immediately see that the links between Alice and Bob are very correlated. And well, let's say much more correlated than what Eve sees in her location. So if we do only the first two steps, like channel feature extraction and quantization, and we measure how many times Alice and Bob agree, how many times they produce the same quantized bits. Remember, these are not the actual keys that are going to be used, but we want to understand from the correlatedness of the channel how often they agree with the generated quantized bits. You see that here, Alice and Bob generated 360 quantized bits from their impulse responses, while Eve didn't agree, never agreed never had the same number of quantized bits. Now you can ask the question of, okay, Eve of course depends on her position, but what if she could do simulations? What if she knows, let's say that we grant some information to Eve, like Alice and Bob range and depth. Let's say that she knows the bathymetry and the sound speed of the area, and she can run a bellhop simulator. And at the end of the day, she can actually simulate the link between Alice and Bob. How would that impact the security of the PLS? So we did that, and here are some results. You see, we're in the same location of Portugal now. We have a more enlarged data set. You see different dates, 7, 8, and 9th of September. On this row here, you have the link from Alice to Bob for the 3 different days. And just below it, you have the simulated Alice to Bob link by Eve using bellhop. And you can see that also I'll do that also for Bob and Alice. And also here you have the simulated link for Bob and Alice. So basically, this is what Eve sees in the second and the 4th line row. You see what Eve understands for these 2 links. And you can compare it with the true measured links for Alice and Bob. And you can see that it is pretty, it's pretty similar. And nevertheless, we want to understand what Eve can do with this level of sophistication. So in the first step, we do the reconciliation protocol. We apply the first and the second step. We quantize the bits, and then what we do as part of the reconciliation protocol, you have Alice here that applies a Reed-Solomon code on the quantized big vector. And so basically encodes the quantized bit vector and gets out a parity bit vector. And that parity bit vector is sent to Bob. So Bob gets the parity back. We are assuming that it's error-free. Basically, in the exercise we do is we don't have any connection losses there in the transmission. So Bob takes the quantized vector, has his own quantized vector, takes Alice's parity bit vector. He applies the decoder, and by applying the decoder, tries to match his quantized bit to Alice. Here, also the application of the Reed-Solomon code is, I mean, we need to be careful that since we don't want Alice to be able to fire a brute force attack at the input of the Reed-Solomon code, so the input bits have to be long enough so that we don't allow Eve to fire a brute force before doing any reconciliation, because we grant the knowledge. Eve is supposed to know the Reed-Solomon code. What is the exact the Reed-Solomon code? Also, she knows what is the parity bits of Bob, so she applies exactly the same algorithm. So how do we ensure? So in order to ensure that the input to the Reed-Solomon code is long enough so that we avoid brute force attacks, we need to group probe transmissions. So we need to basically stack probe exchanges before applying the reconciliation protocol. So doing that with the data that I just showed you, these are some results here by applying 3 different Reed-Solomon codes. We see that they reconcile 2 times for this code and 5 times for this one and 1. So now, at the end of the reconciliation, Alice and Bob, they have a bunch of keys. If they apply different Reed-Solomon codes, they will have a number of different keys. But that's not the end of the story. We need to ensure that Eve cannot do anything with the leaked information that happened during the reconciliation phase. So the output of the output of the reconciliation becomes an input to a hash function, and this is the private simplification. So the output of the hash function is 256 bits, and this is actually the key that we want to potentially use. But before we do that, we need to apply a few randomness tests on the generated key. And here is a bunch of randomness tests that we apply, and these are coming from the NIST statistical test suite. And so we take every key, every reconciled key, we apply 9 tests, and if the results are random with 99% confidence, then we declare this key as random enough and can be used. Otherwise, it's not. So you see that the output of the RS6328 code produced keys that are not random enough. Basically, this parameter has to be 0.01, and since it's below, then we declare this as not random enough. But while the keys that produced by the other 2 codes were random enough, and they can be so that's all. And I really thank you for your attention with an important note. I mean, if not the most important that I said today. So it's our obligation to develop guidelines and harmonics for the harmonic symbiosis of man-made systems with the permanent residents of the ocean. So thank you for the question, so for the attention, and I'm ready to take questions.
Thank you so much. A very, very interesting talk. I see already some questions. So we start with Professor Akildits on the chat, essentially. So essentially he says, I like the regression tree idea, very clear. The output will be mean values of the VERs. So as you know, average values may mislead to wrong conclusion like 0.8 versus 0.01 VERs. The average will be misleading. What is your experience with this problem?
I mean, so you need to. I mean, the decision tree, you can parameterize it with. You can try different nodes, different tree depths, and different the number of the number of leaves. How many leaves do you want to have? So basically, there's a parameterization there in the decision tree that you can play with in order to get, let's say, a result that you like. It's not, I would say, is a trial and error approach there. There is flexibility. This is what I can say. There is flexibility on how you train the tree in order to get, you know, as close as possible to the true BR. Of course, on the other hand, you have the overfitting problem, where you don't want to have let's say you don't want to have very long trees that they overfit the data, and then when if that happens, when in real life you kind of underperform because the environment that you are expecting is not in the model. So it's in my experience, is a trial and error approach. You need to try different trees, different parameterization, different tree depths, and so on. And try and see.
Okay, great. Then there is a second question from Professor. So boosted trees are also interesting. The weights are playing an important role. The selection of these is important. What is your experience with HE values of the weights?
Yes, so it's the same. Again, it's the same answer to Professor Kildis. It's so because this application, so we are in the process of developing the database, because as you so the bigger the database, you know, the more let's say you can have a better trade-off between training and testing phase. So it's a work in progress, what I can say. It's not that I have a definite answer of how to select the number of you know, the number of trees and what is the best approach. It's something that we are working on it, and we are measuring the performance, and we assess basically the performance of the boosted trees. What I can say is that they are easy to implement, and you have all this machinery from Python that you can use, you can play with, and you basically find the solution that better suits your needs. What I like about the boosted trees and the decision trees are very versatile. You can really have a lot of room to play in order to make them suit your needs.
Okay. Great, and then there is a third question. So in your figure,
okay, yes.
Yeah, sure. Exactly. So I am in the chat, right? So third question, in your figure supervised machine learning, you use the box machine learning predicts the BER. Neural networks type.
Sorry. What is the question? I'm in the chat box. I'm trying to.
Exactly. It's in the chat. Actually, it's called third question. Also, if we can unmute Professor Akildis, this would be great.
Okay.
Let's see. I cannot do from my side. So, okay. Anyway, I read again the question.
Yes.
Yeah. So in your figure, supervised machine learning.
So we're looking at slide number.
Slide number is I don't know.
Maybe I should.
I see Ian. Okay, now is a panelist, so I think.
Maybe I should share my screen again.
Ian should be unmuted, right? Can we unmute? Yeah.
So you can see my screen.
Yeah.
Okay. Sorry, where am I? Okay. Yes.
Okay. Now, Professor, you can talk. Great. This is perfect. Yeah.
Hello, Costa.
Hi, hi.
Hello. It's in slide 20 something. Go back to the supervised learning box. Go back. Go back. No, it's yeah. Here. Go back.
Okay.
Back.
You mean?
There is a forward. Here.
Okay. Yes.
Go back. Slide 21. Or slide 20. I don't know. There was this supervised machine learning box. I mean the figure.
Here you mean?
Here, yeah.
Okay.
So you use here machine learning predicts BRs, right?
Yes. Yes.
What are you using there? Like, are you using neural networks type machine learning?
No, this is well. Although this is a very generic, you could use a neural network there to
right, anything, right? Yeah.
You can use anything. So in my case,
okay.
Yes, in my case, I use the decision tree or the boosted tree, but you can use SVMs. You can use other types of machine learning there. It's mainly how I see this working in real life. Basically, you need to have first of all, why it's better if you have the machine learning running in the transmitter and not in the receiver, is because you need to take into account the fact that the channel is changing very fast. So if you have the machine learning in the receiver, and then you say to the transmitter, transmit signal number 5, you need to account for two-way travel time, and this is in that period of time the channel may change. While if you have the machine learning running on the transmitter, you have knowledge of the channel when you get the feedback, and then the channel, and then you have the one-way travel time to hope that the channel doesn't change too much within that time duration. So basically, it's more safe to have the supervised learning in the transmitter than in the receiver. It's the trade-off of travel time versus coherence time of the channel, basically. But yes, you can have whatever machine learning you like there, basically.
You mentioned also this feedback link. The channel conditions may change because of these propagation delay effects, right?
Right.
So how much effects do you have? And
I haven't tested that.
Any,
I haven't. This is something
reiterations in this box that you could somehow adjust the values back in, because then when you select the maximum RI or whatever based on the maximum BRs, and then you send it in, and then it will take forever to come back again, do these cycles internally, iterations. So how can you avoid that, right? Do you get the point?
So, I mean, I can tell you, no, I haven't. I can tell you what is happening in the literature is, what I've seen in the literature is you need to have some prediction of the channel, like some let's say seconds ahead, or if we can say seconds ahead. But you could, for example, the moment when you are ready to transmit, because it takes some time, if you are in a network, you may not be able to transmit the time that you want to transmit, for example. So it's very likely to have outdated channel conditions when you are about to transmit. So if you could do some channel forecasting, in the sense, what do you think? How do you predict the channel? A few seconds ahead. Can you do that? This is also something that I've seen in the literature. But other than that, I'm afraid I don't have I mean, you just hope, you just shoot for the channel that you know, and you will hope for the best.
Thanks for the excellent talk, Costa. Thank you.
Thank you.
We have also some more questions. So one is from Igor. Uday, I have a question on the frequency bandwidth of the communications. I think is referring to one of the first slides.
Okay.
We have an example of ultra wideband systems like a 1 to 10 gigahertz ultra wideband technology with a ratio between high and low frequency of 10, or 20 to 20K sound reproduction system with a ratio high to low frequency of 1000. What are the reasons we do not use UAC with a ratio of 2, larger than 2?
Larger than 2. Well, it could be a hardware issue. You know, the efficiency of your transducer, where you need to. I mean, the higher the band, the longer the band, the lesser the energy that you can put into the water. So it could be a hardware issue. Electronics issue. I would say, and then you have also the frequency absorption issue, where you may have frequency absorption where you won't see the signal.
Okay, Igor.
So let me.
Yes, thank you for the reply.
Yeah.
Wonderful. And then we have 2 questions from Sama. So Sama, in slide 4, is the performance bound based on experiments or on theory?
Based on experiments. It's a rule of thumb. It's not. It's a rule of thumb that you can just apply it, or you can just use it in just that. It's based on. So what happened is slide 4. What happened is that the authors took all the. So basically, what happened is that you see here, these are systems that the authors took into account, and they put on this range rate plot their respective data rates and ranges, and they came up with this plot basically. So it's data driven plot, not any theory driven. So it's more like a practical range rate bound.
Okay, thank you. And then another question, in the machine learning rate selection problem, can we apply a similar approach for the communication mode selection, like acoustic, optical, magnetic induction?
I believe yes, because it's, as I said, it's very versatile. So all you do is you need to have some inputs. So it's a regression, right? So you have a database, you have the inputs. Basically, it could be features coming from the either coming from the acoustic domain or coming from the optical domain, and then you produce an estimate of the BR. So it can be used in different, of course, it can be used for different channels, this machine learning approach.